Physics is fascinating for many reasons. Of course, one reason is that it actually works. But another important reason is that physics gives a sense of plausibility to ideas that would otherwise seem like pure science fiction. Strange objects that feel like they shouldn't exist at all, wormholes, invisibility cloaks, or even ideas like faster-than-light travel. But among all these concepts, the physics idea that has probably captured human imagination the most is parallel universes. According to the many worlds interpretation of quantum mechanics, anything that can happen does happen, just in another universe. So in this highly requested video, I want to explain how the many worlds interpretation works. Is it science? Does it solve any problems? And are parallel universes actually real? That's what we'll talk about today. When you look around you, you see a lot of stuff. Stuff that exists in one particular place. If you're watching this in a pub, maybe stuff that walks around on two legs. But legs aside, everything around you has very definite properties. Objects are not in two places at the same time. They're not smeared across the room. And if they are, maybe you've had enough beer for tonight. But when you look at very small particles, things are very different. Take our good old friend, the electron. An electron is described by something called a wave function, usually written using the Greek letter psi. But the wave function does not tell you where the electron actually is or where it's going. Instead, it only allows you to calculate the probability of what you'll find when you measure it. For example, the wave function tells you the probability of finding the electron in a certain location. But before you measure it, the electron is not in any particular place. It could be in several places at once, or even spread out across the room. According to standard quantum mechanics, often called the Copenhagen interpretation, nothing has definite properties until it is measured. And this applies not only to small particles, but also to large objects. The difference is that large objects are constantly being measured by their environment. Light reflects off them. Air molecules collide with them. However, the Copenhagen interpretation does not explain why some interactions count as measurements and others don't. This is known as the measurement problem of quantum mechanics. What makes quantum mechanics so strange is this sudden switch, from a particle described by a wave function with no definite properties, to a particle with definite properties after measurement. Let's take a photon, a quantum of light, and send it through a beam splitter. And no, we won't send our friend the electron through it. Friends don't let friends go through beam splitters. When a photon passes through a beam splitter, its wave function says it goes both ways at once. This is called a superposition. Let's say each path has a 50% probability. But once you measure the photon on the right side, you instantly know it's not on the left. This means you must update the wave function. Because the wave function only describes probabilities, the outcome of a measurement cannot be predicted with certainty. This is why quantum mechanics is not deterministic. This update of the wave function is often called the collapse or reduction of the wave function, and it is a key feature of standard quantum mechanics. The collapse happens instantaneously, everywhere at once. This is why quantum mechanics is non-local. This strange behaviour is what Einstein famously called spooky action at a distance. The key question is this: is this non-locality just a feature of the theory, or is it a feature of reality itself? If quantum mechanics is fundamentally correct, then reality itself is non-local. But if quantum mechanics is only a description of a deeper underlying reality, one we don't yet see, then that deeper reality could still be local. This idea is known as a hidden variables model. Now, the many worlds interpretation takes a very different approach. Instead of assuming that the wave function collapses, it claims that all possible outcomes of a measurement actually occur, each in its own universe. So rather than a collapse, what really happens is a branching of worlds. In one universe, the particle goes left. In another universe, it goes right. We only experience one branch, so to us, it looks like the wave function collapsed. The biggest challenge for the many worlds interpretation is explaining why an observer only experiences one outcome, even though all outcomes occur. From a practical point of view, many worlds makes exactly the same predictions as standard quantum mechanics. So experimentally, we can't tell the difference. But it leaves us with a mind-blowing idea. Every time quantum interactions happen, which is trillions of times per second, the universe splits. Had a salad for lunch today? In some universe, you had pizza. Maybe with Elon Musk, on Mars. As long as it obeys the laws of physics, it happens in some universe. Does this violate energy conservation? No. Energy is conserved when each branch is weighted by its probability, exactly as in standard quantum mechanics. The biggest problem with many worlds is not that it's wrong, but that it's often claimed to be simpler than the standard interpretation. It isn't. Removing the collapse postulate requires adding other assumptions to replace it. In the end, it does the same job. And despite popular claims, the many worlds interpretation is not local. It is just as non-local as standard quantum mechanics. So, what's the final answer? The many worlds interpretation is not unscientific. It's not wrong. But it's also not provably true. Since we can never observe the other worlds, even in principle, we can neither confirm nor rule out their existence. Whether you believe in parallel universes is ultimately up to you. Thanks for watching. See you next week.